Okay, so you're welcome. Just hold on. Let me share my screen so we can start the lecture. You're welcome to ICH 413. Sorry about this CHM here. It will be changed. I will change it this ICH 413. And this is petroleum refining processes. This is our beginning of this lecture, my own section. So my week one here is on petroleum origin. So the origin of petroleum is still going through some uncertainties because we have different theories supporting petroleum origin. Even though there are a lot of researches and studies that have been devoted to this aspect, we are still, there's still some uncertainties about the origin of petroleum. And so there are two different theories for the origin of petroleum, that of organic and inorganic. We have organic theory supporting origin of petroleum. We have also inorganic origin supporting the origin of petroleum. But we will see which one we're going to stick to and which one is more of a reality. So we're looking at the inorganic origin, which is abiotic origin, which states that hydrogen and carbon came together under a great temperature and pressure below the Earth's surface, and then through a chemical reaction, they together formed oil and gas. And the oil and gas then seep through porous rock deposits in various natural underground traps. It seeps through various porous rocks and deposits in various natural underground traps. This is all about inorganic abiotic origin. And this inorganic and abiotic origin forgets the hypothesis that petroleum is limited in amount, because from this origin, as we see, it's something that it will be happening continuously, renewable. So, but then the truth is that petroleum is limited in amount. And so that is one thing that the inorganic and abiotic origin has forgotten to look at. And so even under this inorganic and abiotic origin, there are several theories that describe the inorganic origin of petroleum and also try to confirm that it's true. So we have the first one is metal carbide theory, which is a theory that supports inorganic origin of petroleum. This theory was developed by a Russian chemist, and it states that the deposition of petroleum is controlled by tectonic activities. and that these tectonic activities occurred during life of sedimentary rock. And then this chemist went further to explain his observations, putting together this theory called metal carbide theory. So the metal carbide deep in the earth reacted with water. This is what the theory is all about. The metal carbide deep in the earth reacted with water at high pressure and temperature to form acetylene, which further condenses to heavier hydrocarbons. And this is the reaction equation, showing the calcium carbide reacting with water to form acetylene. And so I want to explain what the tectonic activity is all about. We said that the petroleum deposition is controlled by tectonic activity, which refers to various processes that shape the earth crust. And those processes include plate tectonics, which involves the movement of the large sections of the earth crust, causing earthquakes, volcanic eruptions, and mountain buildings. So in the mountain building, just a formation of mountain through processes of folding, faulting, and so on. And then earthquake activity is also part of the tectonic activities, which is the sudden release of energy in the earth's crust, resulting in seismic waves, that's vibrations, and ground shaking. So the other one also is volcanic activity, the eruption of molten rock or molten magma onto the Earth's surface. And then the continental shift, the slow movement of continents over millions of years. All these things I've listed to you are the activities referred to as tectonic activities that the Russian chemist is trying to use to describe the metal carbide theory that is one of the origins, inorganic origin of petroleum. So another theory is also in agreement with the tectonic theory. This is volcanic theory, which involves outgassing of the mantle via volcanic activity or eruption. Also, another theory is the earthquake theory, which involves outgassing deep earth mantle via tectonic activities such as faults and so on. And then these activities also is still going on now. So, and then we have serpentinization theory, which states that hydrocarbons is a byproduct that came from metamorphic transformation of the green dark olive mineral. This is silicate mineral that is commonly found in igneous rocks. So it said that this originates from these silicate minerals underground associated with igneous rock. And it is called dark green olivine mineral because of the color, olive green color that it has. And so it's described as dark green. So these are the theories: metal carbide, volcanic, earthquake, serpentinization theory. These are the theories that support inorganic origin of petroleum. So actually, there are overwhelming evidences to support the inorganic origin of petroleum. One of the evidences is geographical location. We realize that most hydrocarbon producing regions are located close to the belt of tectonic activities. So this is one overwhelming evidence that supports this. And another evidence is stability with depth. So if we want to follow what organic theory says, that it's, well, let me leave that, I'll talk about the organic theory later. But This stability instead proves organic theory wrong. So corresponding to organic theory supporters have admitted themselves. Petroleum is a fossil fuel, that is organic theory. And there's never been a real fossil found below 16,000 feet under the earth crust. So why are we then finding crude oil in reservoirs at the feet of 28,000 feet and then 3,000 feet, where there is no fossil remains? So this is another overwhelming evidence that wants to prove organic theory wrong. So let's look at the petroleum origin now based on organic theory. This organic theory origin is the one that is most widely accepted. And this says that the oil and gas are formed from remains of prehistoric plants and animals. As the remains of animals that have been transformed, the remains of animals that once existed and died and then buried on the ground, that is where oil and gas are formed from. And also from plants, where we have, they say coal is formed from there. So remains of plants have been transformed to coal, and that of animals transformed to oil and gas. This is organic origin of petroleum. And it says that the remains were settled into the seas, talking of the fossil, the plants and animals. So when they settle into the sea and they accumulate at the bottom of the sea, then several sediments over time keep piling on top of it, though you have several kilometers of sediment piling on top of the dead organic plants or animals. And then over a few millions of years, the layers of the organic materials were compressed under the weight of the sediment above it. So the increase in pressure and temperature with the absence of oxygen changed the mud, sand, and silt or sediment into rock, and also changed organic matter into kerogen. So further burial and heating transform the kerogen via cracking method into petroleum and natural gas. This is all what organic origin is talking of. I'll explain to you what kerogen is. We'll see it in the next slide. It's a solid form of petroleum somehow. So we have the overwhelming evidence also. Just like the inorganic origin has some overwhelming evidence to prove that actually petroleum is formed from inorganic origin. Also, organic origin has overwhelming evidences. One is that the presence of brine, seawater or salt water with petroleum. Where you get petroleum, you always find in it some brine water, some brine. And petroleum, the other evidence is that petroleum is found only in association with sedimentary rock. Remember, I just mentioned that underground, that under the heat and pressure, high pressure, that the sand, the silt, the sediment form into rock, sedimentary rock, while the buried plant and animal, dead plant and animals form oil and gas. So there's this evidence here that petroleum is formed only, we always find petroleum only associated with sedimentary rock. So this is one overwhelming evidence. So there is no petroleum associated with igneous or metamorphic rock. This is also disproving the evidence of disproving the origin by inorganic. In all times, all petroleum is associated with sedimentary rock and not with igneous or metamorphic rock that inorganic origin is talking of. Then another evidence is that polarized light passing through all petroleum resources undergo a rotation that is similar to that of all organic oils. Same rotation that happens with petroleum of polarized light is the same that is found also, that's similar to all organic oils. So this is another strong, overwhelming evidence. So also that molecules of hydrocarbon are thought to be similar to that of the organic matter. This is another evidence that molecules of hydrocarbons are thought to be similar to that of organic matter. Then another evidence is that organic carbon found in plants is depleted into carbon-13 due to photosynthesis process. So this proof of also, of course, carbon-13 is also you get it in hydrocarbons. So in dead organic matter, it is further depleted due to radioactive decaying. The same depletion also is found in petroleum and natural gas. So this is another overwhelming evidence. And so people, based on people now go more towards the origin of organic origin, that petroleum formation is based on organic origin. Petroleum is a fossil fuel, which means it's derived from the remains of organic materials. So this is what is believed for it to be. In other words, petroleum results from a number of chemical reactions that occur to materials that once were alive. So in most cases, liquid petroleum was once zooplankton or algae that settled to the bottom of the sea or lake and was then buried under the sediment. And the sediment ensured that no oxygen was able to reach the decaying organic matter. And this set the stage for the formation of oil. We're looking at formation of petroleum based on organic origin. So in most cases, the organic matter goes through several changes to take, it can take thousands or millions of years. So it goes through several changes. As sediment continues to pile up and increase pressure on the organic matter, it is first changed into a waxy solid. First changed into a waxy solid that I mentioned before, that is called kerogen. That is the first stage of the formation of the petroleum. In fact, this material is currently being mined in many cracking processes because it can, through chemical conversion, be made into liquid and natural gas, petroleum and natural gas. So you can crack the kerogen to form petroleum and natural gas. And the kerogen is formed in a process that is called diagenesis. Diagenesis. So essentially, the heat and pressure breaks down organic compounds. Talking of how the kerogen is formed by the diagenesis process, heat and pressure break down organic compounds and various other organic acids and lipids, proteins, carbohydrates, and so on to form long hydrocarbon chains. These long hydrocarbon chains called geopolymers. Geopolymers. So geopolymers are the basis of the kerogen. Geopolymers are the basis of this kerogen that we're talking of. So diagenesis is a critical mechanism in the formation of coal and is the first of several processes that are necessary to convert solid hydrocarbon to liquid petroleum. Diagenesis converts solid petroleum to solid hydrocarbons to liquid petroleum. So the addition of greater heat is necessary to convert the kerosene to liquid or gaseous hydrocarbons. And the process takes some time. So the combination of high temperature and pressure is necessary to carry out the endothermic process known as hydrocarbon pyrolysis, which sometimes is referred to as cracking. I think maybe you'll come across it in your ICH 311. So that is hydrocarbon pyrolysis. So hydrocarbon pyrolysis actually is irreversible. That means once the hydrocarbon is formed, the liquid hydrocarbon is formed, it remains the liquid. It cannot be converted back to the solid form, the kerosene form. So it's irreversible. It's one-way process. So this is why oil deposits can exist below the surface of the earth for millions of years without changing, to just remain there as liquid. The liquid hydrocarbons, they are really just formed by breaking of the bonds of longer chains. Generally in chemistry, we know that larger molecules are more likely to be solid. Smaller molecules are more likely to be either liquid or gas. So long hydrocarbon chains are solid, while the medium chains from 5 to 25 carbon long chain are liquid. And then, so smaller chains that are below 5 carbon atoms, they tend to be gaseous. They be gases. And this is why you have your gasoline or your fuel at 7 or 8 carbons. We have it as liquid. While methane, which has only 1 carbon atom, is a gas. Versions of cracking are used in industry to create everything from charcoal to carbon fiber to biofuels through cracking, different cracking processes. Process is often used in oil refinery to break down the less valuable heating oil molecule. The crude oil, those ones that are very high carbon contents, are more solid. To break them down to useful ones, they pass through this cracking process. So molecules of 25 carbons per chain on average can be broken down to smaller ones that are of more value, those ones of 7 and 8 carbon chains that can be used as gasoline. Now, oxygen. What part does oxygen play in petroleum formation? Importance of oxygen in petroleum formation. Oxygen is really, really critical to many processes. The absence is absolutely critical to the formation of hydrocarbons. What I mean here is that when oxygen is present, several things can happen during that formation of hydrocarbons. At the surface, when oxygen material is first laid down, when organic material is laid down, and the presence of oxygen means the presence of bacteria, which will quickly consume and decay the material before it will have any chance to be buried under the sediment. So if it is not decayed and is buried under the sediment, of course, that's a positive indication that it will form petroleum. But if it is decayed, it cannot. And the decay is caused by the presence of oxygen. freeing the presence of bacteria, consume and decay the organic material before they can get buried for formation of crude oil. This is why most petroleum deposits were once at the bottom of the sea lake, often one with very low oxygen content. I think you can even see this, you look at offshore and onshore. Most of the drilling offshore, petroleum is found at the bottom of the sea or lake. So, and then that is where sediment had time to accumulate before too much decay could occur in the presence of oxygen. If oxygen is present, besides derailing the early stage of kerogen formation, it can also lead to other things, like formation of acid and other molecules instead of the formation of crude oil. It can form something else. And these are usually detrimental to the formation of hydrocarbon and can even reverse the formation that has already occurred. The presence of oxygen can do that. So the levels of oxygen that are not high enough to prevent hydrocarbon formation, it can still be a problem. Low levels of oxygen can lead to buildup of toxic nitrogen oxide compounds, as well as sulfuric and sulfurous acid. All these act as contaminants in petroleum. And because of so much contaminants, due to low oxygen level, this makes refining of petroleum much more expensive and more difficult. So that's another negative effect, even if the oxygen is present in low concentration. So let's look at petroleum composition. Composition of petroleum. Many people presume that petroleum is really similar to gasoline or petrol. That's only that it is not as pure, so one needs to refine it a bit to make it pure. Yes, in a way, somehow, but not quite so. Actually, chemical composition of petroleum in a raw state can vary extremely. You can have those that are very heavy, you can have those that are really light, that is close to what we described here earlier, in the first sentence. And the variation is the reason why petroleum composition differs so much in color, in viscosity, between the crude oil fields and geographical areas. What this means is that at different crude oil fields, you will have the petroleum composition varying. And they vary in composition, they vary in other properties like color and viscosity in different oil fields and also different geographical areas. For instance, the oil we have here in Nigeria will vary, be different from what we have in Saudi Arabia because of those difference in composition. So petroleum or crude oil, when it is raw, in the raw form, they contain several chemical compounds. And the most prolific one is the hydrocarbons themselves. And it is hydrocarbons that gives petroleum composition that's is the hydrocarbon content that gives petroleum combustible nature. Very, very flammable. Is that hydrocarbon content that causes that. So although the composition of petroleum contain many different elements, the key compounds in petroleum are carbon. We have 93 to 97% of carbon. In petroleum, we have 10 to 14% of hydrogen. We have 0.1 to 2% of nitrogen. We have 1 to 1.5% of oxygen. And we have 0.5 to 6% of sulfur. And then we also have some trace metals that make up the remaining percentage of the petroleum composition. And the actual overall properties of each different petroleum source, they are defined by the percentage of the 4 main hydrocarbons that are found within petroleum. 4 main hydrocarbons, the percentage of these 4 main hydrocarbons determine the overall property of the different petroleum from the different sources. The percentage of these hydrocarbons can vary greatly, giving the crude oil a quite distinct compound personality depending on the geographic region. So, and these 4 main hydrocarbons that we're talking of are paraffins, the naphthenes, aromatics, and the asphaltics. Paraffins make up 15 to 60% of petroleum. Naphthenes 30 to 60%, aromatics 3 to 30%, and then remaining is the asphaltic, the very solid, more strong, solid form of it with longer hydrocarbon chains. So depending on which one is much predominant, then the hydrocarbon can be classified according to which one is much predominant in that particular petroleum. If it is paraffins that are more predominant, maybe 60% is paraffin and other ones will be smaller percentage, then it will be a paraffinic crude oil. So also with the other ones. So you can name it according to which of these 4 hydrocarbons are more predominant. And the composition of petroleum is defined as laid out above, like I've just explained to you, and it gives the petroleum its properties. So raw petroleum normally is dark brown color, sometimes almost black, although we have some fields that are greenish petroleum and some yellowish, and all this based on the composition of that particular petroleum. So depending upon the field and the way the petroleum composition was formed, the crude oil will also differ in viscosity. Some are more viscous and some are lighter, depending on the composition. At the extreme ranges, petroleum can be almost solid. If it's like this, if it's almost solid, it then requires significant investment of resources to refine into a usable state. Other than bitumen, of course, you know, bitumen is solid, so it has to be refined to other things that are more usable than just bitumen. And then it takes a lot of investment to do this. At the other end, we're talking of the heavy one that needs to be refined, putting in so much investment to refine into useful products. On the other end, you have those ones that are really light, clear, fluid, flowing, resembling kerosene or gasoline, our fuel. And then this type needs very little refining for it to be usable as fuel. Generally, petroleum is measured in volumes. And for some composition of petroleum, it's not cost effective to refine into fuel. For some composition, the lighter and less dense petroleum composition with a compound which contains higher percentages of hydrocarbon is much more profitable to be refined into fuel. And on the other hand, the denser one with less flammable level of hydrocarbon and sulfur, these ones are expensive to refine into fuel, but they are more suitable to be refined for plastic manufacturing. In this case, that type is passed to the petrochemical section of the plant, while the refining section handles the fuel, and then the petrochemical handles these other organic chemicals, plastics, and so on. Unfortunately, the reserve of light petroleum, that is the light crude oil, are severely depleted. Already it's almost exhausted. The light ones severely depleted. So refineries are forced now to refine refine and process those ones that are more heavy, the heavier crude oil and the bitumen. So refineries are now forced to refine those ones because the light ones that are easy to be refined are so much depleted. So in some cases, the refining process, you need to remove carbon and add hydrogen. That is when we're looking at the more heavy hydrocarbons. So there might be need to remove carbon and add hydrogen. Then doing this also is adding extra cost to the steps of the refining process. And so going through this, changing the compound by removing carbon and adding hydrogen. So this, and also the increase in refining costs, has led to the high price of gasoline across the world. There are modern techniques of well identification. We're looking at modern techniques of well identification. When I'm talking of well, I'm talking of oil well. As I said, that the light petroleum and those ones that could easily be found and you could easily identify where they are, all those ones have been exhausted. So there's need for other techniques to explore and find where we have oil well for drilling. So deciding where to drill may be as much of an art as a science. So as we go on, you will see what this means. The primary search for hydrocarbon frequently begins with observation of the surface terrain, such as location of faults at the surface. They are very important because they indicate where potential structural traps may lie beneath the Earth's surface in reservoir rocks. Observation of anticlines is another type of structural trap, also indicate potential traps at some depth. Naturally existing crude oil seeps, they blacken the ground and spread rainbow films on streams. In some time past, in the Niger Delta, when the oil was discovered, you could see some streams, you see something like rainbow on top of the stream. These are natural existing crude oil seeps. They blacken the ground. You could see, go to your farm, and then you see a particular part of the farm black. And then it means there's crude oil there. And then maybe a stream around your village, see something like rainbow on top of it. That is another direct evidence that is useful, to identify where you have oil well. But most of such places have long ago been identified and explored. And so you cannot find those ones again. That is the reason for looking for other techniques to be able to explore for oil well where you'll be able to drill without making mistake. So, and some of the modern exploration techniques are what I have here, and we're going to discuss them today. There are three primary methodologies used to find hydrocarbons in the subsurface. One is called geophysical technique, another one is remote sensing technique, and another one is called wildcatting. So let's look at the geophysical technique that is used for petroleum exploration. This one utilizes several equipment to measure some properties like electrical current, gravitational and magnetic anomalies, what is not supposed to be, heat flow, geochemical relationships, and density variations from deep within the earth. So each of these techniques that are just listed under the geophysical techniques records a different set of characteristics which can be used to locate hydrocarbons beneath the surface of the earth. And so there are several methods under geophysical techniques that we want to discuss. One of them is called seismic surveys. I'm going to discuss 4 of these methods under geophysical techniques. One is called seismic surveys. It uses vibration to provide a picture of subterranean rock formations at depth, often as deep as 30 feet below ground level. And this vibration is induced by an explosive charge or sound generating equipment. So seismic survey uses vibration that is induced by explosive charge. They use explosive charge or sound generating equipment. The explosive charge is mainly used when you're carrying out the seismic exploration on land, and that of sound generating equipment is mainly used when you're carrying out the exploration offshore. And so we have, under seismic surveys, we have 2, one on land and one offshore. So, and this is accomplished by generating sound waves downward into the earth crust, which reflects off various boundaries between different rock strata. So we look at the one on land. On land, the sound waves are generated by small explosive charges embedded in the ground, or they use also what is called vibrator trucks. Sometimes these trucks are referred to thumpers, and these thumpers, they shake the ground with hydraulically driven metal parts. So human eyes can barely hear the thump, but the frequency generated penetrates the earth crust. Human eyes can barely see, can barely hear, but that frequency that is generated penetrates deep into the earth crust. And the echoes are detected by electronic devices called geophones. These geophones receive the reflected sound waves, and the data are recorded on magnetic tape, which is further printed to produce a 2-dimensional graphic illustrating the subsurface geology. Now, offshore. The offshore surveys are conducted in a bit different manner. Offshore, boats tow cable containing hydrophones in the water, which are similar to geophones on land. Sound waves used to be created by dynamite before, but that method used to kill the variety of sea life. A lot of fish will die and so on because of using dynamite in the water to create sound waves. So the most acceptable method today is to generate sound waves using pulses of compressed air. And this creates large bubbles that burst beneath the water surface and create sound. So the sound waves travel down the sea floor, penetrate the rock beneath, then return to the surface where they are intercepted by the hydrophones. In this case, for the land, we use geophones, but in the water, you see, the offshore is hydrophones. So the processing and illustration is the same as that of the dry land method, only that this one, we use hydrophones, and then we also use a different method to create the sound wave. So in this type of survey, sound waves are sent into the earth, whether it's from offshore or whether it is from on land. The sound waves are sent into the earth where they are reflected by different layers of rock. The time for them to go and reach that rock is measured as a function of time, and how long it goes to hit the rock and come back to the surface, that time interval determines how far the reservoir or the rock or where you have the oil is. The measurement reveals how deep the reflecting layers are. The greater the time interval for it to go and hit that layer and come back, the deeper the rock layer. So the distance is deeper if the time it takes to go and return is longer. So this technique also determines the type of rock that is present, because different rocks transmit sound waves differently. So apart from the fact that it's going to tell you the time, how, or the depth of the layer of the oil, it will also tell you what type of rock is there. If it's a different rock from sedimentary rock, of course, you know that there's no oil there, because crude oil is almost always associated with sedimentary rock. And then for seismic survey, more sophisticated seismic surveys, they use three-dimensional analysis. So the recorded data is processed by computer, and the results are detailed three-dimensional pictures of the formations and structures below the surface. This process is really expensive. It's in the order of $30,000 per mile that you go deep, $30,000 per mile. So it's expensive. But even though it's expensive, it is still very, very good to carry out, because the cost of drilling oil well runs into multiple millions of dollars. So if you don't carry out the exploration and you just assume that the oil is there, spending multiple millions of dollars is much more painful than just spending $30,000. So it's important to carry out accurate seismic surveys, and this is a good investment since it will help you to locate prospects and minimize dry holes. Dry hole is just nothing is there, just drill for nothing. So in general, seismic surveys can be carried out without disturbing people or damaging the environment, whether they be carried out on land or water. It's a primary tool used by exploration geologists to locate hydrocarbon prospects. There are a number of other geophysical techniques that I mentioned to you before outside seismic survey. We have magnetometers, and we have gravimeters. We have geochemical prospecting, magnetometers, gravimeters, geochemical prospecting. Geochemical prospecting is a relatively new technique. So let's look at magnetometer. It's a device that is pulled behind aeroplane. We fly it, aeroplane, on a long cable that detects variations in the Earth's magnetic field. Sedimentary rocks generally have low magnetic properties compared to other rocks. So when they detect low magnetic properties, then it's an indication that there's sedimentary rock there and there is oil. The other one is gravimetry. A gravimeter measures minute differences in the pull of gravity at the surface, at the Earth's surface. Differences in the pull of gravity at the surface of the Earth. Even as minute as the difference could be, gravimeter will measure it. And then mapping these differences reveals large masses of dense subsurface rock, which allows geologists to have a better idea of the structures below that place. Then the other method still under geophysics, under that is geochemical prospecting. It uses sensitive instruments to detect minute quantities of gases that have seeped upwards from petroleum deposits. Uses sensitive instruments to detect minute quantities of gases that have seeped upward from petroleum deposits. This is relatively a new technique, but it's one that is gaining wider acceptance now. So we now have the other method, remote sensing. Remote sensing uses aerial photographs to locate a map, locate and map surface features. So in this case, it's satellite imagery that is being used because it shows large areas on the surface of the Earth. So even though the photographs are taken from several hundred miles up there in the space, still able to show some features, just only few feet in size into the surface of the Earth. Satellite imagery, they not only indicate what the human eyes can see, also they reveal some variations in soil moisture, mineral and vegetation distribution, soil type, of which all these are of great importance. They are important pieces to the exploration puzzle. Yes, Ashiru, yeah, you want to ask a question? You can unmute and ask. Yes.
Ma, we have another class, ma.
Oh no. Okay. It's time. It's not yet. Okay, it's time already. Okay, so, next time you have to come on time. So we'll just start immediately because those few minutes we lost would have just covered these few slides that remain. So I think I'll have to stop here since you have another lecture. In the next class, we might have to also look at this one and then go to the next section. So do you have any question? Somebody just joined. I don't know why the person just joined 2 minutes ago, 2 minutes to the close of the lecture. Class rep, Mary, you know the people that are here. I need to have them, the list. Okay, so ending this lecture now. See you next week, Tuesday. Bye.